For our project, we created a procedurally generated Minecraft settlement with a focus on pathfinding as well as biome and terrain adaptation for our submission to the 2021 Minecraft GDMC competition. This involved placing a variety of houses with paths connecting them while adapting the block types used to the biome and terrain of the given area. Our settlement is also themed around gardening and farming. What makes our project interesting is that we decided to try to adapt our settlement to the environment as much as possible, rather than adapting the environment to the settlement. This gives a much more human-like feel to the settlement and a more natural aesthetic, which was one of our goals for this project. Following images are some examples of our generated settlements. When placed on water, platforms are built for the houses and bridges are made to connect them. In specific biomes like desert biomes, biome-specific blocks are used as building materials. How we decided to divide up the work. Brianna focused on the pathfinding and placing of the paths, biome and water detection along with the adaptation of the buildings accordingly, house design for one of the houses, decorating the settlement with a fence, gardens, and flowers, along with the majority of the slideshow. I worked on the algorithm that found the ideal plots of land in the given terrain to build on, house placement, house design for 2 houses, and the project trailer. Problem description. These are some of the problems that we had to deal with for this project. Finding mostly flat land to plot houses on. In doing so, we had to keep track of the coordinates of doorways and plots for the pathfinding algorithm. Pathfinding between houses, choosing which houses to connect, avoiding large height changes in paths if possible, making sure paths do not run through buildings or go outside the build area, and avoiding wasted time when there is no possible path. Placing paths in the world, making the paths look nice by making them have a relatively consistent width and height. Biome detection and adaptation, detecting the biome of the given terrain and choosing which types of blocks to use based on the biome. Water detection and adaptation, placing all houses, paths, and decorative structures on a platform when they are above water. Faced with the problem of creating a village that adapts to the terrain, we decided to create an algorithm that searches for plots of land within the build area that are most suitable for building on. We felt that taking advantage of the natural landscape as much as possible when placing houses would give a more natural aesthetic to the village. Place plots methodology. The place plots function uses a window the size of the current selected house design to scan the landscape within the build area. It records the height of all the blocks within the window and stores them in a list along with recording the Y coordinate of the highest block in the window. If there are less than 3 heights within the list, it checks to see what the difference in height is. If it is sufficiently small enough, we will place the house in this location using the highest Y coordinate that we recorded and the X and Z coordinates from our window. Calling the house is on water function, we determine whether or not to place supports for the house. The X and Y coordinates of all the blocks in the window are added to the plots list so that the path can avoid these areas. The position of the doorway is added to the doorway list so that the path knows what to connect. A random house style is then selected for the next plot. Once this is completed, the current X value is increased. The code will continue to loop through the area, searching for more plot locations. Place plot pseudocode. Current X is the current X coordinate at the start of the window. Current Z is the current Z coordinate of the start of the window. W is the width of the current house design, and L is the length of the current house design. Current I is the index to select the house design. Dimensions contains a list of the house dimensions and is accessed by current I. Doorways contains the X and Y coordinates of all doorways. And plots contains X and Y coordinates of all blocks occupied by a building. The first 2 loops are used to move the window throughout the build area to search for potential plots. Heights is a list that holds the different heights of the plot. Highest stores the highest y-coordinate in the plot, and map stores the frequency of heights in the plot. The next two loops scan each block in the window and get the height and add them to the map. Then updates highest if a new highest coordinate is found. We then loop through the map and check for non-zero values. We add these values to the height list. We check heights and see if it has less than 3 elements. If it does, we check the difference in these elements to ensure that there is not a drastic height difference within the plot. If the height difference is sufficiently small, we build the house based on the current eye, which determines the design we use. We add door positions to doorways, add plot coordinates to plots, and we generate a random current eye to determine the next house design. We increase current X by the width of the current house design, and then we check to see if the house is on water and build a platform underneath the house. If heights has more than 3 elements, or the difference in elements is more than 1, we will increase the current X by 1 and search again for the next area.
In order to create paths between the houses in our settlement, we decided to use the A* algorithm with the diagonal Manhattan distance as our heuristic. We chose this algorithm since, due to the use of the heuristic, it is typically faster than other search algorithms such as BFS, as it expands less nodes. Therefore, it is efficient enough to be used for larger build areas. Also, this algorithm is flexible and can adapt well to different terrain features and placements of houses. We also wanted to allow for diagonal paths to make the paths look better and more realistic. Therefore, we use the diagonal Manhattan distance since it is admissible for diagonal movement. During our search, we also place a limit on the size of the closed list in order to avoid wasted time and infinite loops when there is no possible path. This limit is based on the size of the given build area. Here we have the pseudocode for our A* pathfinding algorithm. The actual code for this algorithm can be found in the pathfinding.py file. It is a typical A* algorithm with the addition of our limit on the size of the closed list. We used a priority queue based on the fcost of a node for the open list, and an array that stores xc positions for the closed list. We first add the start state to the open list and then create our limit based on the build area size. Then while the open list is not empty and the length of the closed list is less than or equal to the limit, we search the build area for a path. This involves popping the node with the minimum cost from the open list and then checking if this node is at the goal. If so, then we return our path that we found. Then we check if the node is in the closed list, since if it has already been expanded, then we do not need to expand it again, so this saves time. If it is not in the closed list, then we will add it and expand the node, adding its successors to the open list. A subproblem for our pathfinding was avoiding large height changes in paths so that they are easily walkable for players. In order to achieve this, we added a height penalty to our pathfinding. If the height of the parent node differs from the height of its child node by 2 or more, then we add a penalty to the g-cost of the child node based on this height difference. We can see that this works in the image shown where the path goes around the tall placement of ice instead of going over it. Also, while expanding nodes, we check if each new child node is both within the build area and not within any plots where houses are placed. We can see this in the pseudocode for our expand function, used in our A* search algorithm. In this function, for each of the possible 8 actions corresponding to the 8 directions, we find what the new coordinates of the node would be if we take that action. Then we check if this state is outside the build area or inside a plot or already in the closed list in order to improve efficiency and prevent invalid paths. Then we calculate the height difference between the parent and child node. If it is greater than or equal to 2, we add a height penalty multiplied by the difference. Otherwise, we use the normal g-cost. Then we calculate our heuristic, create the new node, and add it to the open list if it is not already in there with a lower G cost. In order to choose which houses to connect with paths, we use the diagonal Manhattan distance heuristic to estimate which houses are closest to each other and connect the closest ones. Each house connects to two other houses, except for the first and last houses placed, which each only connect to one other house. The method to do this uses an array called doorway list, which stores for each doorway its coordinates and the indexes of other doorways in the doorway list that it's connected to. Before the doorway is fully connected to the path, it stores none in place of the indexes. Basically, given the current doorway we want to connect, we iterate through each other doorway in the list. First, we make sure that the doorway is not already fully connected. Then we check to see if these two doorways are already connected, and if so, continue. Otherwise, we find the distance cost using our heuristic and check if it is lower than the lowest cost so far. At the end, we simply return the doorway we found to be the closest to the given doorway. In order to place our found paths in the world, the first step is to check if the current section of the path is along the x-axis, along the z-axis, or diagonal. We do this by comparing the coordinates of the current block in the path to the previous block. For non-diagonal sections, we attempt to place a block on both sides of the main block at the same height as the main block in order to make the path have a width of 3 and a consistent height. For diagonal sections, we check all 8 blocks surrounding the main block and place the ones that aren't in any plots. So given a path, for each block in the path, our place path function first compares the coordinates of the current and previous blocks and passes the section type to the place path helper function. In this function, we first check if the main block is inside any plots, and if so, do not place it. Then, if the section is along the x-axis and there is at least one adjacent block free, we find what the middle block of our path should be by checking if blocks with adjacent z-values are in the plot list or not. Then we find the height of our found middle block and place it along with blocks on both sides of it. If no adjacent blocks are free, then we just place the one block. For sections along the z-axis, it is the same except with x and z switched. Then for diagonal sections, we simply place the adjacent blocks in any of the 8 directions that aren't in any plots. Lastly, we have an example of how our paths are placed between houses. Next, I'll describe how we achieved our biome detection. We focused on 4 main biome types. These types are the plain/forest type biomes, desert biomes, badlands biomes, and icy biomes. In order to detect the biome of the given terrain, we started by creating arrays that store the common block types found in each of these biomes. Then we iterate through a small percentage of the blocks in the area, getting the block type of each of them. We only go through a portion of the blocks since iterating through all the blocks in the build area would take too long, especially for larger areas. Also, the terrain is typically uniform enough that this method will most often give the correct biome. While iterating, we check if the found block type matches any of the common block types for the biomes. If so, we increase the score for that biome by 1. Once we are done iterating over the blocks, we check for a few special cases. If the score for every biome is low, then we default to the plains biome since it is the most common one and looks good in many different biomes. Also, if there is a certain amount of ice, we automatically default to the ice biome. This prevents ice biomes with some snow-covered grass or sand from being misdetected as another biome. Lastly, if none of these special cases occurred, then the biome with the highest score is our detected biome. Here is some pseudocode showing this process. The actual code is located in the biome.py file. First, we initialize the scores for each of these biomes to 0. Then we iterate through 1% of the top layer of blocks in the build area and update the scores based on these blocks as shown. Then we check for special cases where either all the scores are less than a certain threshold, so we default to plains, or if there is more than a certain threshold of ice, so we default to ice. Otherwise, we simply return the biome corresponding to the highest score. Once we detect the biome, adapting to it is easy. We create a dictionary storing the different build materials that should be used depending on what the biome is. Then we simply index the dictionary based on the found biome while building to place the correct block types dynamically. An example of one of these dictionaries is shown that we used in order to change the main material of one of our houses based on the biome. The features that adapt to the biome this way include each of our 3 houses, which each have unique materials specified for each biome, as well as all of the paths. All the fire items such as lanterns, torches, and campfires are the sole versions in ice biomes to avoid melting the ice, and the normal fire versions otherwise. Lastly, all the decorative items such as fences and plants adapt to the biome. For instance, the fence is made out of sandstone in desert biomes. Next we have a pseudocode example where we're placing a lantern at some XYZ location and using the lantern type dictionary indexed with the biome in order to use the correct type of fire in the lantern for this biome. The actual code that does biome adaptation is located everywhere blocks are being placed, which are the house, plot, and decorate.py files. Then we have a screenshot of a settlement in a Badlands biome that shows how the houses and paths adapt to the biome by using materials that match the terrain. Additionally, our flower gardens turn into greenhouses in certain biomes by conditionally placing glass around them instead of a fence. We also adapted our settlements to water, so they will look good and be functional even when there is water in the area. The way we did this is simple. Before placing houses or decorative items such as gardens, we check if there is water in the area. If so, we will place them on top of a platform as shown in the image. Similarly, for paths, we check if each block in the path will be above water. If so, instead of placing a normal path block, we will place a platform block instead. Then we have some pseudocode showing how this works in our code. So for any given house area, which is the area underneath the base of the house, if this area contains any water, we will build a platform slightly larger than the house area and then build a house on top of the platform. For paths, for any given block in the path, if that block will be above water, we build a 1x1 platform in place of a path block.
This video demonstrates our village being generated in a plains biome. Once all the buildings have been placed, the paths start connecting all the doorways, which connects the village. After this, the fence is placed around the village, along with decorations within the village. This video showcases when our village is generated completely on water. It has wooden supports underneath and wooden bridges connecting the houses. In further detail inside the houses, we chose to include lots of decorations to fit the aesthetic we were going for, as well as many blocks necessary for the player to actually live in the house. We chose this balance so that while the houses looked good, they were also functional for the player. This is our smaller house design, which has more decorations, but the upstairs still has some necessary functional blocks needed by the player. This video demonstrates our village being generated in a desert biome. As you can see, the houses are built with biome-specific blocks, sandstone in this case, and this is our third house design. Again, we focused on a mixture of visually pleasing, and functional blocks for the player to use. Things we tried to do but did not finish in time. Making sure that there are no height changes greater than or equal to 2 in the paths. We added a height penalty so that this doesn't happen very often, but it can still happen. How we tackled the GDMC categories. Adaptability. We avoided flattening the land too much by placing houses on relatively flat areas in the given terrain. We also adapted the building materials to the specific biomes that they were in. We also adapted the structures and paths to be on platforms if over water. Functionality. We avoided large height changes in paths to make them easily walkable by players. We also placed useful items like beds and crafting tables, along with anvils and ender chests in some of the houses. Narrative. We created a settlement with an overall theme of gardening and farming. All the houses have many flowers and plants in their design, and one of them has a connected farm. We placed gardens and greenhouses near the entrance of the settlement to have other flowers and plants around. Aesthetics. Designed aesthetically pleasing houses with many decorations on both the interior and exterior. We also placed fences, gardens, and plants around the settlement to add to the aesthetic. How we feel we did in each of the GDMC categories. We think we did well in each of the GDMC categories, particularly in the adaptability and aesthetics categories, since these are where we focus most of our efforts. Our settlements are extremely adaptive to the given terrain as they do not change the given terrain very much, and they look good in many different biomes and environments. How we arrived at the final version of our code. We decided to go with our plot finding approach to placing houses as we wanted to maintain the environment as much as possible. The best way to accomplish this was to find the areas we wouldn't have to alter very much in order to place a structure. For our pathfinding, we decided to use the A-star algorithm with the diagonal Manhattan distance heuristic, as it was efficient enough to be used for larger build areas and proved to be flexible and adaptable to the environment. It also allowed for diagonal paths, which was important for maintaining the natural look we were going for. Conclusion. Our goal was to make an algorithm that could create a village that looked like it belonged in the terrain. We feel that we have accomplished this goal by altering the color palette of our buildings based on their biome and fitting them into the land with minimum alterations. The downside of this approach is that it relies on there being numerous suitable build areas in the terrain. However, when there are suitable build areas, it results in a very natural looking village. The pathfinding adds to this natural look by avoiding stiff repetitive paths and having a realistic structure. Future improvements. Adding more features to the biome adaptations, such as creating different building designs for different biomes in specific, or expanding to include other biomes like a mountain biome. Making sure there are no height changes greater than or equal to 2 in the paths. Adding more unique buildings and decorations to the settlement to give it more variety. Adding more to the narrative through placing items like books and signs. Improving building integration into the terrain so that it remains as natural as possible. Adding slabs to accommodate any height difference in the path. And creating smaller house designs for areas with few suitable build plots.